What if I told you the universe isn't just expanding, it's breathing? Picture this: every galaxy, every star, even the empty darkness between them, all pulsing in a slow, cosmic rhythm, inhaling and exhaling over billions of years. It sounds like something from a science fiction novel, but this might be the key to unlocking one of the greatest mysteries in modern physics: dark energy. That mysterious force pushing the universe apart faster and faster, making up nearly 70% of everything that exists, yet hiding in plain sight. What if it's not some abstract, unchanging force, but something far more alive, something more like breath? For centuries, we've thought of the universe as a cold, mechanical place, planets orbiting, stars burning out, galaxies drifting apart. But what if we've been missing the bigger picture? Ancient civilizations believed the cosmos was alive, cyclical, even conscious. Now, cutting-edge science is starting to catch up. Theories are emerging that suggest dark energy could be the universe exhaling, stretching space-time outward in a vast, slow breath, only to one day inhale again, pulling everything back in a cosmic reset. The implications are staggering. It would mean everything we think we know about the fate of the universe, about time, about reality itself, might need to be rewritten. So let's take a journey into the unknown. Over the next few minutes, we'll explore mind-bending ideas from quantum physics to string theory, from black holes behaving like cosmic lungs to the eerie echoes of ancient myths that predicted it all. We'll examine the evidence, question assumptions, and dare to ask, is the universe truly alive? And if it is, what does that mean for us? Strap in, because by the end of this, you might never look at the night sky the same way again. Dark energy isn't just some abstract concept, it's the dominant force in our universe, shaping its destiny in ways we're only beginning to grasp. Think about this: nearly 70% of everything that exists isn't stars, planets, or even dark matter. It's this invisible, enigmatic energy woven into the fabric of space itself. And here's the strange part: it doesn't behave like anything else we know. Matter clumps together under gravity, forming galaxies and clusters. Radiation travels through space, carrying energy. But dark energy, it's eerily uniform, stretching the universe apart like an unseen hand pulling at the seams of reality. What makes dark energy so baffling is how it defies intuition. Imagine blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots move apart. Now, picture that expansion speeding up over time, as if some invisible force were pumping more air into the balloon without anyone touching it. That's dark energy in action, accelerating the universe's expansion without any obvious source or mechanism. Scientists call this acceleration the cosmological constant, but the truth is, we still don't know why it exists or how it works. Some theories suggest dark energy might be a property of space itself, a kind of background energy inherent to the vacuum. Others propose it's a dynamic field, changing over time like the ebb and flow of a cosmic tide. But what if it's even more fundamental? What if dark energy isn't just a static force, but part of a larger, rhythmic process like the universe breathing in and out? Ancient philosophies often describe the cosmos as cyclical, with periods of creation and dissolution. Modern physics might be stumbling toward a similar idea, just dressed in the language of equations and data. The evidence for dark energy comes from observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe. Each of these clues points to the same conclusion: something is pushing the universe apart faster than gravity can pull it back together. If this acceleration continues, the cosmos could end in a big freeze, where galaxies drift so far apart that the sky goes dark and the universe becomes a cold, empty void. But if dark energy isn't constant, if it's more like a breath, then maybe this expansion is just one phase of a grander cycle. Consider the way your own breath works. When you exhale, your lungs empty, but that's not the end, it's just the prelude to the next inhale. Could the universe operate the same way? Right now, we're in the exhale, with dark energy driving expansion. But if the breath turns, if the universe begins to contract, everything we think we know about its fate could change. The mystery of dark energy isn't just about what it is, it's about what it means for the story of the cosmos. And that story might be far more alive than we ever imagined. What if the universe isn't just expanding but breathing? Picture a cosmos that doesn't simply stretch outward forever, but pulses in a slow, rhythmic dance of expansion and contraction, like the rise and fall of a chest. This isn't just poetic imagination, it's a serious hypothesis gaining traction among physicists. The idea flips our understanding of dark energy on its head. Instead of a relentless force pushing galaxies apart until they vanish into cold isolation, dark energy might be part of a grander cycle, the universe exhaling only to one day inhale again. Think of it like this: when you blow up a balloon, you're adding energy to stretch its surface. But what if the balloon could breathe on its own, expanding and contracting without your hands? That's the essence of the breathing universe theory. Dark energy, in this view, isn't a static background force, it's dynamic, waxing and waning over cosmic timescales. Right now, we're in the exhale phase, with space stretching faster and faster. But just as breath turns, the theory suggests this expansion could eventually slow, halt, even reverse. Galaxies might someday begin rushing back toward one another, drawn by a cosmic inhale we can't yet detect. This cyclical vision isn't entirely new. Ancient Hindu cosmology spoke of universes breathing in and out over epochs, with each cycle lasting trillions of years. Even some early 20th century scientists like Richard Tolman toyed with the idea of an oscillating universe, but modern physics brings fresh evidence to the table. Observations of distant supernovas show dark energy's strength might not be perfectly constant, it could fluctuate subtly over time. If those fluctuations follow a pattern, like the slow filling and emptying of lungs, it would support the breathing universe model. The implications are staggering. A cyclical cosmos means the Big Bang wasn't a one-time event. It could have been preceded by countless others, each followed by a big crunch as the universe inhaled. Black holes might play a role too, acting like cosmic lungs that absorb and release energy in ways we're only beginning to understand. String theory adds another layer, suggesting hidden dimensions could be where this breathing motion truly originates, with our observable universe just one ripple in a higher dimensional rhythm. Critics argue that without direct evidence of contraction, the theory remains speculative, but supporters counter that we're like goldfish in a pond, observing only a tiny fraction of the universe's lifespan. If the exhale lasts billions of years, the inhale might be too distant for our instruments to detect yet. Future telescopes, like the Vera Rubin Observatory, could spot clues in the way galaxies cluster or how dark energy's pressure changes over time. Even gravitational wave detectors might one day catch echoes of a prior cosmic cycle, like faint whispers from a universe that came before. The beauty of this idea isn't just in its scientific audacity, it's in how it bridges the cold equations of physics with something almost organic. If the universe breathes, it blurs the line between cosmos and life, suggesting existence itself might be more fluid, more alive than we ever dared imagine. Long before telescopes or particle accelerators, ancient cultures peered into the night sky and saw something modern science is only beginning to grasp: a universe that breathes. Hindu scriptures describe cosmic cycles called kalpas, each lasting billions of years, where universes dissolve and reform like waves on an endless ocean. The Mayans calculated time in vast spirals, their long count calendar tracking epochs of creation and destruction. These weren't just myths, they were precise observations of cosmic patterns, encoded in stories and stone. Today, physicists like Roger Penrose explore conformal cyclic cosmology, a theory eerily similar to those ancient visions. It proposes that our universe's distant future, a cold, empty expanse stretched thin by dark energy, could become the seed for a new Big Bang. The mathematics suggest a startling possibility. When all matter evaporates into radiation, the universe resets, and time itself loops back to a new beginning. What's remarkable isn't just the similarity between these ideas, it's the mechanism they imply. Dark energy, often portrayed as a mindless force, might be the cosmic heartbeat driving this eternal rhythm. Imagine a pendulum swinging between creation and dissolution. On one side, dark energy accelerates expansion, scattering galaxies like dandelion seeds in the wind. On the other, its influence could wane, allowing gravity to pull everything back in a fiery embrace. The Hindu concept of pralaya, the dissolution of the universe, mirrors modern hypotheses about vacuum decay, where quantum fluctuations trigger cosmic rebirth. Even the Mayan Popol Vuh describes worlds being folded up like a blanket before new ones unfold, a metaphor that aligns with Penrose's idea of conformal rescaling, where the universe's geometry stretches and resets. Skeptics dismiss these parallels as coincidence, but the evidence mounts. Recent studies of the cosmic microwave background reveal faint concentric rings, potential echoes of collisions with a pre-Big Bang universe. If confirmed, these Penrose circles would prove that our cosmos isn't the first iteration, just the latest breath in an endless cycle. Meanwhile, quantum physicists note that dark energy's behavior resembles a phase transition, like water turning to steam or ice, a process that, in nature, is always reversible. Could the universe's expansion be one half of a deeper thermodynamic cycle? The real magic lies in how these ideas bridge time and culture. A Mayan astronomer charting Venus's path and a physicist modeling dark energy with supercomputers are asking the same question: does the universe remember its past? The answer might lie in the subtle fingerprints ancient light carries, or in the way dark energy's pressure fluctuates over eons, hinting at rhythms older than stars. Whether through sacred texts or equations, humanity keeps returning to one truth: the cosmos isn't a static stage but a living, breathing entity. And if the ancients were right about cycles, perhaps their wisdom holds other clues waiting for science to catch up. Einstein once scribbled a tiny term into his equations, a mathematical fudge factor he called the cosmological constant. His goal was simple: to keep the universe static, balancing gravity's pull with an invisible push that prevented collapse. But when Edwin Hubble proved the universe was actually expanding, Einstein famously dismissed his own idea as a blunder, calling it his greatest mistake. What he couldn't have known was that this so-called error would resurface nearly a century later as the key to one of cosmology's deepest mysteries: dark energy. Here's the twist. When astronomers discovered in the late 1990s that the universe wasn't just expanding but accelerating, they realized Einstein's constant might not have been a mistake after all. It was as if the universe had been hiding a secret in plain sight, a repulsive force embedded in space itself, perfectly mimicking the cosmological constant. But what if this force isn't constant at all? What if it ebbs and flows like the rise and fall of breath? Imagine blowing up a balloon with a slow leak. At first, it inflates steadily, but over time, the air escapes unevenly, causing unpredictable bulges and contractions. Now, picture the universe as that balloon, with dark energy acting like the air, sometimes pushing outward with more force, sometimes less. This idea, known as quintessence, suggests the cosmological constant isn't fixed but dynamic, changing over cosmic timescales. Some models even propose it could flip from repulsive to attractive, turning the universe's exhale into an inhale. The implications are profound. If dark energy fluctuates, it could mean Einstein's blunder was actually a stroke of genius, just premature. His constant might not have been wrong, merely incomplete. Modern theories like vacuum metamorphosis take this further, suggesting dark energy could evolve based on quantum fields we haven't yet detected. It's as if Einstein planted a seed that's only now bearing fruit, revealing a universe far more dynamic than he ever imagined. Critics argue that without direct evidence of these fluctuations, the theory remains speculative, but supporters point to subtle anomalies in supernova data, hints that dark energy's strength might vary slightly across space and time. Future missions like the European Space Agency's Euclid telescope aim to map these variations with unprecedented precision, potentially uncovering the universe's hidden rhythm. The real beauty of this idea lies in how it transforms our view of cosmic history. Instead of a one-way march toward cold emptiness, the universe might be pulsing, its expansion and contraction dictated by a deeper, more organic logic. Einstein's blunder could turn out to be the first clue in a puzzle we're only beginning to solve, a reminder that even the greatest minds sometimes underestimate the cosmos's creativity. At the smallest scales imaginable, empty space is anything but empty. Quantum mechanics reveals a seething, bubbling froth where particles and antiparticles blink into existence for fleeting moments before annihilating each other. This isn't just theoretical, we've measured it. Place two metal plates incredibly close together in a vacuum, and the quantum foam between them actually produces a measurable force, the Casimir effect, proving that so-called empty space is alive with energy. Now imagine this microscopic chaos writ large across the cosmos. What if these quantum ripples don't cancel out but somehow accumulate, their tiny pushes and pulls scaling up to shape the very fabric of spacetime? This wild idea suggests that dark energy might emerge from the collective behavior of quantum fluctuations, like trillions of fireflies synchronizing their flashes to create what looks like a steady glow. Normally, these particle pairs vanish as quickly as they appear, but some theories propose that in the vast stretches between galaxies, they might leave behind traces of energy. Over cosmic distances and timescales, these traces could add up, creating the repulsive force we observe pushing the universe apart. Picture the surface of a pond on a windy day. Individual ripples seem random, but together they create waves that move the entire surface. Similarly, quantum jitters might be driving the universe's grand expansion. The math behind this gets even stranger. Quantum field theory suggests that vacuum energy should be vastly stronger than what we observe as dark energy, by a factor of 1 followed by 120 zeros. This staggering discrepancy, called the cosmological constant problem, has baffled physicists for decades. One possible resolution: the universe's expansion itself might be damping down these quantum effects, like a cosmic feedback loop where spacetime's stretch smooths out the microscopic chaos. In this view, dark energy isn't some exotic substance but the leftover quantum noise that couldn't be cancelled out, a faint echo of the universe's smallest vibrations shaping its largest structures. Critics point out that linking quantum fluctuations to cosmic expansion remains speculative without direct evidence. But intriguingly, Certain quantum gravity models predict that spacetime itself might have a granular structure at the tiniest scales, a kind of pixelation of reality. If true, the universe's expansion could be the macroscopic manifestation of these fundamental grains relaxing over time, like stretched fabric smoothing out its wrinkles. Future experiments with ultra-precise atomic clocks or gravitational wave detectors might catch hints of this spacetime granularity, bridging the quantum and cosmic realms. What makes this idea so compelling is how it ties together physics' greatest puzzles. The same quantum rules governing electrons in atoms could be sculpting galaxy clusters. The uncertainty principle, which says we can't precisely know a particle's position and momentum, might also determine the fate of the cosmos. It's a reminder that the universe operates on all scales simultaneously, from the briefest quantum flicker to the slowest cosmic breath. As we peer deeper into both quantum foam and galactic superclusters, we might discover they're not separate phenomena but different notes in the same eternal song. Empty space isn't the barren void we imagine. It crackles with an invisible energy so fundamental, it might hold the key to dark energy itself. Quantum physics reveals that what we call a vacuum isn't empty at all, but a turbulent sea of virtual particles flickering in and out of existence. These fleeting quantum fluctuations generate what's known as vacuum energy, a background hum of the universe that could be driving its accelerating expansion. Think of it like static on an old television, seemingly random noise, but beneath it lies a hidden pattern shaping everything we see. The connection between vacuum energy and dark energy isn't just poetic, it's a serious scientific proposition. According to quantum field theory, every cubic centimeter of space, no matter how empty it appears, contains a staggering amount of latent energy. But here's the puzzle. When physicists calculate how much energy this quantum foam should produce, the numbers are astronomically larger than what we observe as dark energy. It's like expecting a hurricane and feeling only a breeze. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved mysteries in physics. Some theorists suggest the answer lies in the way vacuum energy might fluctuate over cosmic time. Instead of being a static force, it could pulse like a heartbeat, growing stronger or weaker across eons. Imagine blowing across the surface of a cup of hot tea. At first, your breath creates steady ripples, but as the tea cools, the patterns change. Similarly, vacuum energy might have behaved differently in the early universe, its influence waxing and waning as spacetime expanded. This could explain why dark energy seems to dominate now, billions of years after the Big Bang. If vacuum energy isn't constant but dynamic, it could mean the universe's expansion rate isn't fixed, either accelerating in some eras, slowing in others, like the inhale and exhale of a living system. The implications are profound. If vacuum energy drives cosmic expansion, then the quantum world isn't just a quirky sidebar to reality, it's the engine of the universe. String theory adds another layer, proposing that hidden dimensions could be leaking energy into our observable space, subtly altering vacuum energy's effects. Even black holes might play a role, their immense gravity warping the quantum foam around them, creating localized ripples in dark energy's influence. Testing these ideas isn't easy, but next-generation telescopes like the Nancy Grace Roman Space Telescope aim to measure dark energy's behavior with unprecedented precision. By observing how the expansion rate changes over billions of years, we might catch vacuum energy in the act of shifting gears. Other experiments, like ultra-sensitive quantum sensors, could detect minute variations in the energy of empty space here on Earth. What's mesmerizing about this idea is how it turns nothingness into something alive. The vacuum isn't passive, it's a seething, dynamic canvas where the universe's fate is written in quantum whispers. And if those whispers really do control the cosmos's breath, then the greatest force in existence might be hiding in plain sight, woven into the fabric of space itself. String theory paints a picture of reality far stranger than our everyday experience, suggests a cosmos where the three dimensions we know might be just the surface of something deeper. According to this framework, tiny, curled-up dimensions could exist at every point in space, folded so tightly they're invisible to us, like the intricate patterns woven into a carpet's fibers. These hidden dimensions aren't static. They vibrate, resonate, even pulsate in ways that could ripple across the fabric of our observable universe. And here's where things get truly mind-bending. What if dark energy isn't a force confined to our familiar dimensions at all, but the echo of these higher dimensional spaces breathing in and out? Think of it like this. Imagine blowing across the mouth of a bottle to create a sound. The pitch you hear doesn't come from the air outside. It's generated by vibrations inside the bottle's hidden cavity. Similarly, dark energy's effects in our universe might be the sound of these compact dimensions oscillating in ways we can't directly see. String theorists propose that the energy tied up in these vibrations could leak into our three-dimensional space, manifesting as the mysterious push driving galaxies apart. It's as if the universe has a hidden engine humming in dimensions beyond our perception. The math behind this idea is both elegant and daunting. In string theory, the way these extra dimensions curve and vibrate determines fundamental constants like gravity's strength or the mass of particles. Even slight changes in their geometry could alter how energy propagates through spacetime. Some models suggest that as the universe expands, these dimensions might slowly decompress, releasing energy that counteracts gravity, a process we'd observe as dark energy. Others speculate that higher dimensional membranes in the bulk of hyperspace could collide or flex, sending shockwaves through our reality. Critics argue that without experimental proof, these ideas remain in the realm of mathematical beauty, but supporters point to subtle clues. If dark energy's strength has varied over cosmic history, it might reflect shifts in these hidden dimensions' configuration. Future particle colliders or precision tests of gravity could uncover anomalies that betray their presence. Even the cosmic microwave background might hold imprints of higher dimensional physics, like shadows cast on a cave wall. What's thrilling is how this reshapes our quest to understand dark energy. Instead of searching for some exotic particle or field in our familiar dimensions, we might need to listen for the universe's hidden harmonies, the notes played in dimensions we're only beginning to fathom. If string theory is right, then dark energy isn't just a mystery to solve, but a message from realms beyond our sight, waiting to be decoded. Black holes aren't just cosmic vacuum cleaners. They might be the universe's respiratory system, inhaling and exhaling energy in a rhythm that shapes the cosmos. Picture this, a supermassive black hole at the heart of a galaxy, devouring stars and gas in a violent feast. But here's the twist: black holes don't just consume. They also exhale, blasting out jets of energy and radiation so powerful they can carve voids in intergalactic space. This cycle of absorption and expulsion mirrors the way lungs take in oxygen and release carbon dioxide, fueling a larger system. Now, imagine this process scaled up across billions of galaxies, with black holes collectively regulating the universe's expansion like a vast network of cosmic bellows. Recent simulations reveal something astonishing. Black holes might not just be passive players in dark energy's drama. Their growth and activity could be intertwined with the universe's accelerating expansion. When black holes merge, they release gravitational waves, ripples in spacetime that carry energy across the cosmos. Some theorists propose these waves could subtly influence dark energy's behavior, like pressure changes in a lung affecting breath. Even more intriguing, the energy black holes radiate as they evaporate. Hawking radiation might counteract dark energy's repulsive force in localized regions, creating pockets where expansion slows. It's as if the universe has a built-in thermostat with black holes balancing its breath. The math behind this idea is as elegant as it is profound. Einstein's equations show that black holes warp spacetime so severely that time nearly stops at their edges. This extreme environment could act as a cosmic pressure valve, modulating how dark energy propagates through the universe. Observations of quasars, supermassive black holes powering brilliant galactic cores, hint that their energy output correlates with large-scale cosmic structures. Where quasars are abundant, galaxies cluster differently, almost as if their black holes are sculpting the universe's expansion on a grand scale. Critics argue that black holes are too sparse to influence something as pervasive as dark energy. But supporters counter that their cumulative effect over billions of years might be profound. Think of it like rainfall shaping a mountain range. One raindrop does nothing, but over eons the collective force carves canyons. Similarly, black holes' combined energy output could be gently steering cosmic expansion in ways we're only beginning to detect. Future gravitational wave observatories, like the Laser Interferometer Space Antenna, might catch whispers of this black hole respiration, revealing how these cosmic giants truly interact with the fabric of reality. What's mesmerizing is how this reframes our place in the universe. If black holes are cosmic lungs, then galaxies and, by extension, stars and planets are like oxygen molecules cycling through a vast organism. The atoms in your body might have once passed through the fiery maw of a black hole, only to be exhaled into the stellar nursery where our sun was born. This isn't just poetry, it's a radical new lens through which to see existence, where the largest and smallest scales of reality are linked in an eternal dance of breath. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic saga? The Big Bounce theory dares to rewrite our origin story, proposing that the universe doesn't explode into existence once, but cycles through endless rebirths. Picture a cosmic accordion, expanding and contracting over trillions of years, with each collapse not spelling doom but renewal. In this radical vision, dark energy plays the hero, not just pushing galaxies apart but preventing total annihilation. When gravity's pull becomes too strong, dark energy could be the universe's safety valve, halting the crush of a big crunch and sparking the next Big Bang. It's as if the cosmos has a built-in resurrection mechanism, rising from its own ashes like a phoenix woven into the laws of physics. The elegance of this idea lies in how it solves one of cosmology's biggest puzzles: what came before the Big Bang? If the universe bounces, there's no need for a mysterious starting point, just an infinite loop of expansion and contraction. Ancient Hindu texts describe this as the cosmic dance of Shiva, where creation and destruction are two steps in an eternal rhythm. Modern physics echoes this with equations showing how a collapsing universe might not reach infinite density, but instead rebound when quantum forces kick in, like a ball bouncing off an invisible trampoline. Dark energy could be the key to that rebound, its repulsive force growing stronger as space contracts, until it overpowers gravity and sets the stage for rebirth. Evidence for this cyclical universe might be hiding in plain sight. Some models suggest that black holes from a previous cosmic cycle could survive a bounce, carrying imprints of a past universe into our own. Others point to anomalies in the cosmic microwave background, strange patterns that resemble scars from a pre-Big Bang collision. Even the distribution of galaxies across the sky could hold clues, with certain large-scale structures aligning in ways that suggest a prior phase of cosmic history. The most tantalizing hint: dark energy's strength appears fine-tuned to allow just enough expansion for stars and galaxies to form before a potential contraction, almost as if the universe calibrated itself for endless renewal. Critics argue that without direct observation of a bounce, the theory remains speculative, but proponents counter that the alternative, a universe that emerges from absolute nothingness, is equally mysterious. The Big Bounce offers something profound, a cosmos without beginning or end, where every ending seeds a new beginning. Future telescopes might settle the debate by hunting for gravitational waves from the Big Bang's earliest moments. If those waves carry a specific signature, a telltale imprint of a prior contraction, it could be the smoking gun for a cyclical universe. What's breathtaking about this idea isn't just the science, it's the philosophy. A bouncing universe means the atoms in your body have likely cycled through countless cosmic incarnations. The gold in your jewelry might have been forged in a galaxy that existed trillions of years ago, only to be reborn in our universe's stellar furnaces. It's a humbling reminder that we're not just observers of the cosmos, but participants in its grand, unending rhythm. Entropy is the universe's relentless march toward chaos, the reason ice melts, buildings crumble, and stars eventually burn out. It's the cosmic rule that disorder must always increase, a law so fundamental it feels inescapable. Yet dark energy behaves like a cosmic wildcard, pushing galaxies apart with a repulsive force that seems to defy this inevitable decay. If entropy is the universe winding down, dark energy might be the counterweight, an exhale so powerful it creates pockets of order amidst the chaos. This cosmic tug of war could hold the key to whether reality ends in heat death or something far more mysterious. Picture a campfire on a cold night. As the wood burns, embers scatter into the darkness, entropy in action, energy dispersing into the void. But what if some unseen force gathered those embers back into the flames, reigniting the fire against all odds? Dark energy's repulsive push might be doing something similar on a galactic scale. As it accelerates the universe's expansion, it doesn't just stretch space, it dilutes entropy's grip, thinning out matter and energy so that disorder spreads more slowly. In regions where dark energy dominates, galaxies aren't just drifting apart, they're being pulled into a state where entropy's usual rules are rewritten. The math behind this is as beautiful as it is strange. Thermodynamics says entropy rises because there are more ways for things to be disordered than ordered. But dark energy's influence changes the playing field. Imagine a deck of cards being shuffled normally. They'll end up in random order. But if someone keeps adding blank cards to the deck, the chance of finding meaningful sequences actually increases. That's the paradox dark energy introduces. By stretching space-time, it might be creating conditions where complexity can persist longer than entropy alone would allow. Some theories even suggest that in a universe dominated by dark energy, pockets of low entropy regions could emerge naturally, like eddies in a flowing river. Critics argue that dark energy doesn't truly reverse entropy, it just delays the inevitable. But supporters counter that the interplay between these forces might be more nuanced. Black holes, for instance, are entropy powerhouses, yet their evaporation via Hawking radiation could release energy in ways that temporarily offset disorder. Even the quantum vacuum, seething with particle pairs, might fluctuate in ways that locally defy entropy's arrow. If dark energy modulates these processes, the universe's fate might not be a slow fade to darkness, but a series of ebbs and flows, like breath sustaining life against decay. The implications are staggering. If dark energy and entropy aren't locked in a zero-sum game, but instead dance in dynamic balance, then the cosmos might harbor surprises we've yet to imagine. Far from a lifeless void, the universe could be a place where order and disorder trade roles across epochs, weaving a story far richer than the cold equations suggest. And if that's true, then the ultimate fate of reality might not be written in stone, but in the delicate interplay between expansion and entropy, between breath and chaos. The faint glow of the cosmic microwave background isn't just ancient light. It's a cosmic fingerprint carrying secrets from the universe's first breath. This afterglow, lingering from just 380,000 years after the Big Bang, holds subtle temperature variations, patterns so delicate they're measured in millionths of a degree. But within these whispers of heat and cold lies something extraordinary, the potential signature of dark energy's rhythmic push and pull. Imagine the early universe as a pond struck by a pebble, its surface rippling outward. Those ripples froze into the cosmic microwave background as space expanded, leaving behind a snapshot of the universe's infant pulse. Now, scientists are decoding these patterns like astronomers reading celestial tea leaves, searching for clues that dark energy wasn't just present. It was already shaping spacetime's expansion in those primordial moments. What makes these temperature fluctuations so revealing is their scale. Certain patches appear stretched or compressed in ways that don't quite match predictions based on gravity alone. It's as if an invisible hand was already tugging at the fabric of the cosmos, subtly altering how matter clustered in the universe's youth. Some theorists propose these anomalies could reflect dark energy's early influence, not as a constant force, but as a dynamic presence waxing and waning like breath. The European Space Agency's Planck satellite mapped these variations with unprecedented precision, revealing faint but persistent irregularities that align with models where dark energy's strength evolves over time. If confirmed, this would mean the universe's expansion hasn't been a steady acceleration, but a variable rhythm like lungs filling and emptying at changing speeds. Even more tantalizing are the so-called cold spots, regions of the cosmic microwave background that are unusually large and chillier than expected. One such anomaly, spanning nearly 2 billion light-years, defies standard cosmological explanations. Could these be cosmic scars from an earlier cycle of expansion and contraction, like echoes of a universe exhaling before our Big Bang? Roger Penrose's conformal cyclic cosmology suggests just that, proposing that these cold spots are imprints of supermassive black holes from a prior cosmic era, their gravity warping the newborn universe's light. While controversial, the idea underscores how the cosmic microwave background might be more than a relic. It could be a palimpsest, layered with hints of deeper cosmic cycles. The next generation of telescopes, like the Simons Observatory in Chile, aim to probe these patterns with even finer resolution. By measuring the polarization of this ancient light, how its waves oscillate, scientists hope to distinguish between competing dark energy models. Some predict specific swirls in the polarization that would only arise if dark energy fluctuates cyclically, while others look for statistical anomalies in the temperature distribution that could reveal a breathing pattern. The data might even uncover evidence of cosmic inflation's end, the moment the universe's initial exponential expansion gave way to the more sedate growth we see today, like the pause between an inhale and exhale. What's striking is how these observations bridge the unimaginably vast and the infinitesimally small. The same quantum fluctuations that spawned galaxies also left their mark in the cosmic microwave background, meaning the universe's largest structures and its oldest light are bound by the same physics. If dark energy's fingerprint is indeed hiding in this primordial glow, It wouldn't just solve a cosmological puzzle, it would reveal the universe as a dynamic, almost living entity, its breath etched in the oldest light we can see. And that light, having traveled for over 13 billion years, might finally be ready to tell us how the cosmos truly moves. Look up at the night sky, and you're seeing more than just scattered stars. You're witnessing the universe's breath frozen in time. Zoom out far enough, and galaxies don't drift randomly. They form vast, intricate webs with shimmering threads of star clusters stretching billions of light years, connected by invisible filaments of dark matter. This cosmic architecture isn't just beautiful, it's eerily reminiscent of biological structures, like the branching networks of neurons in a brain or the delicate alveoli in a lung. The resemblance is uncanny enough to make scientists wonder, could these galactic patterns be the universe's way of exhaling, imprinting its rhythm onto the fabric of space itself? The key lies in the way these structures form. Simulations of the early universe show how tiny quantum fluctuations, random ripples in density, got stretched by cosmic expansion, becoming the seeds for galaxy clusters. Gravity amplified these ripples, pulling matter into dense knots along filaments, leaving vast voids between them. But here's the twist. Dark energy's repulsive push seems to sculpt these voids, stretching them wider as the universe expands. It's as if every filament is a crest in a cosmic wave, with dark energy determining how far apart those crests spread. The result, a universe that looks less like a static sculpture and more like a living lung mid-breath, its structure expanding and thinning with each exhalation. What's mesmerizing is how closely these patterns mirror fractals, geometric shapes that repeat at every scale, from snowflakes to ferns. The universe's web-like structure does the same. Zoom in on a single galactic filament, and you'll find smaller clusters arranged in the same branching pattern. This self-similarity suggests an underlying rhythm, almost as if dark energy's influence operates like a universal tempo, setting the pace for how matter organizes itself. Some theorists even propose that the spacing between superclusters could encode dark energy's respiratory rate, a cosmic metronome ticking over billions of years. The evidence isn't just theoretical. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing how their distribution matches predictions of dark energy's role. Where models omit dark energy, the cosmic web looks denser, more tangled, like a lung compressed. Add dark energy's push, and the voids widen, the filaments stretch, mimicking inhalation. Even the way galaxies move within these filaments hints at a larger rhythm. Some flow smoothly along the cosmic highways, while others seem to stall at nodes, like air pausing at the turn between inhale and exhale. Critics argue that these patterns could arise from gravity alone, no breath metaphor needed. But supporters counter that dark energy's fingerprints are all over the details, the exact ratios of void sizes to filament lengths, the way galaxies align along curved paths rather than straight lines. Future projects like the Dark Energy Spectroscopic Instrument aim to measure millions of galaxy positions and velocities, essentially creating a 3D movie of the cosmic web's motion. If those movements match the subtle undulations of a breathing universe, expansion speeding up here, slowing there, it could be the closest we've come to feeling the cosmos's pulse. The profound implication: we might be living inside a structure as dynamic as a lung, with galaxies like oxygen molecules riding the universe's breath. And if that's true, then mapping the cosmic web isn't just about charting space, it's about listening to the rhythm of existence itself. One of the most terrifying scenarios in cosmology is known as the Big Rip, a hypothetical future where dark energy doesn't just accelerate the universe's expansion but grows infinitely stronger over time. Picture this: first, galaxies will be torn apart as the space between them stretches faster than light can bridge. Then stars would be ripped from their orbits. Eventually, even atoms themselves would be shredded as the fundamental forces holding matter together are overpowered by dark energy's relentless push. It's the ultimate cosmic apocalypse, leaving behind a cold, empty void where nothing can ever form again. But what if this nightmare scenario isn't the end, just the universe taking its deepest possible breath before inhaling once more? The key lies in reimagining dark energy not as a static force, but as a dynamic one that ebbs and flows. Most models treat dark energy's strength as constant, but some theories suggest it could evolve in unexpected ways. Phantom energy, an extreme form of dark energy, would grow more potent as the universe expands, creating a feedback loop where faster stretching leads to even stronger repulsion. This runaway effect is what fuels the Big Rip scenario. Yet there's a twist: if phantom energy follows certain quantum rules, its growth might hit a limit, like a spring stretched to its maximum tension before recoiling. At that critical moment, the universe's violent exhale could reverse, with dark energy's repulsion flipping into an attractive force, pulling everything back in a cosmic inhale. This idea isn't pure speculation. Certain variations of string theory and quantum gravity allow for dark energy's equation of state, the way its pressure relates to its density, to change over time. In these models, the Big Rip becomes less of a finale and more of a turning point, the moment when the universe's expansion reaches its peak and contraction begins. Think of it like a rubber band snapping back after being stretched too far. The mathematics even hint at a cyclical pattern. Each rip and rebound could spawn a new universe with slightly different physical constants, creating an endless cascade of cosmic resets. The evidence for this wild idea is still circumstantial, but tantalizing clues exist. Some observations of distant supernova show slight deviations from the expected brightness, suggesting dark energy's strength might not be perfectly uniform. If these variations follow a pattern like the slow build and release of tension, they could signal the universe's breathing rhythm. Even the cosmic microwave background's temperature fluctuations might hold hints, with certain anomalies aligning with models where dark energy's influence peaks and wanes over trillion-year timescales. What's fascinating is how this reframes our existential dread. A big rip sounds like the ultimate destruction, but in a breathing universe, it's just one phase of a grander cycle. The same force that could tear atoms apart might also be the spark for cosmic rebirth, like a forest fire clearing the way for new growth. This perspective doesn't just change how we see the future, it reshapes our understanding of dark energy itself, from a mindless destroyer to a vital participant in the universe's unending rhythm. And if that's true, then even the most violent cosmic events might be part of a deeper, almost organic pulse, the universe breathing in, out, and beginning again. Time has always felt like a one-way street. Eggs don't unscramble, shattered glass doesn't reassemble, and memories only move forward. This irreversible flow, known as time's arrow, is rooted in entropy's relentless rise, the universe's tendency toward disorder. But dark energy throws a cosmic wrench into this tidy narrative. If the universe's expansion isn't just a one-time explosion but part of a rhythmic breath, with contraction following expansion, then time's arrow might not be fixed at all. Imagine a cosmic inhale so powerful it reverses entropy itself, turning the universe's clock backward like a rewinding film reel. The idea of time reversing isn't just science fiction. Physics equations are symmetrical. They work just as well whether time flows forward or backward. It's only entropy's rise that gives time its direction. But in a contracting universe, the rules could flip. As space collapses, matter and energy would compress, entropy could decrease, and the universe might literally retrace its steps. Stars would unburn their fuel, scattered particles would reassemble into atoms, and the cosmic microwave background's fading echo would grow louder again. This wouldn't just be a visual rewind. Conscious beings in such a phase might experience time in reverse, remembering the future and forgetting the past. Here's where dark energy's role gets even stranger. If its repulsive force weakens and becomes attractive during contraction, it wouldn't just pull galaxies back together, it could reset the thermodynamic clock. Some models suggest that at the moment of maximum contraction, the universe would bounce, with time's arrow flipping direction as a new cycle begins. Think of it like a pendulum swinging. As it reaches the peak of its arc and starts falling back, the forces acting on it invert. Similarly, dark energy might act as the universe's pendulum, governing not just space's expansion but time's very flow. Critics argue that entropy's reversal is mathematically possible but practically unimaginable, like unscrambling an egg by perfectly reversing every molecular collision. Yet supporters point to quantum gravity theories where time's arrow is more fluid, especially near extreme events like a big crunch. Even black holes, with their ability to warp time near their event horizons, hint that time's direction isn't as absolute as it seems. If dark energy's fluctuations could alter the fabric of spacetime on cosmic scales, why not time's arrow too? The implications are dizzying. A universe where time breathes in and out would mean that every ending is also a beginning, every death a rebirth. The distant future of one cycle could become the distant past of another, with civilizations rising and falling in an endless loop. It challenges not just physics but philosophy. What does now even mean if time is cyclical? Future experiments might test these ideas by probing the nature of dark energy's influence on cosmic acceleration. If its strength varies in ways that align with cyclical models, we could be one step closer to understanding time's true nature. Until then, the universe keeps its deepest secrets hidden in the rhythm of its breath, expanding, contracting, and perhaps even rewinding itself in a dance older than stars. Nature has a curious habit of repeating its patterns across wildly different scales. The branching veins of a leaf mirror the tributaries of a river delta. The intricate web of neurons in your brain looks eerily similar to the cosmic web of galaxies spanning the universe. These aren't just coincidences, they're signatures of how complexity emerges from simple rules, whether in biology or cosmology. Now take that idea further. If the universe truly breathes, expanding and contracting like a living lung, could it share even deeper traits with biological systems? Parallels are too striking to ignore. Think about how living organisms regulate themselves. Your body maintains a delicate balance: temperature, oxygen levels, even the rhythm of your heartbeat, all fine-tuned to keep you alive. The universe might operate on a similar principle. Dark energy's push against gravity's pull creates an equilibrium, controlling the rate of cosmic expansion like a thermostat regulates a room. Galaxies cluster along filaments like nutrients flowing through capillaries, while black holes act like cellular organelles, processing energy and shaping their environment. Even the universe's large-scale structure, with its vast voids and dense superclusters, resembles the porous architecture of bone or lung tissue, optimized for efficiency across incomprehensible scales. This isn't just poetic analogy. Scientists use the same mathematical tools to model galaxy formation as they do to study fluid dynamics or bacterial growth. Fractal patterns, those self-repeating shapes found in ferns and coastlines, also appear in the distribution of matter across the cosmos. The way galaxies spin and cluster follows equations startlingly similar to those describing how schools of fish move or how forests spread. Some researchers even suggest that the universe could meet certain criteria for a living system. It grows, it metabolizes energy through stars converting matter into radiation, and it arguably reproduces through black holes birthing new spacetime in their interiors. The most profound implication: if these parallels reflect a deeper unity, then the laws governing life might not be separate from the laws governing the cosmos. They could be different expressions of the same fundamental principles. Ancient philosophies often describe the universe as a living organism, from the Greek concept of the world soul to indigenous cosmologies that speak of earth and sky as interconnected beings. Modern physics, in its own language, might be circling back to that same intuition. Of course, not all scientists embrace this view. Critics argue that anthropomorphizing the universe risks conflating metaphor with mechanism. Yet even the staunchest reductionists admit there's power in these comparisons, not as literal biology, but as a lens to ask better questions. If dark energy behaves like a regulatory force, could it have analogues in cellular feedback loops? If galaxies evolve like ecosystems, could they have something akin to life cycles? These aren't just whimsical thought experiments. They're bridges between disciplines, sparking collaborations between astrophysicists and biologists that might one day crack open new understandings of both life and the cosmos. What makes this perspective so exhilarating is how it transforms our place in the universe. We're not just passive observers of a dead mechanical void. We're participants in something vast and dynamic, perhaps even alive in ways we're only beginning to fathom. The atoms in your hands, the stars overhead, the dark energy stretching space itself, all might be part of a grand, breathing whole, pulsing to rhythms older than time. Consciousness has long been the ghost in the machine of physics, an elusive phenomenon we can't quite pin down, yet undeniably central to our experience of reality. Now imagine taking that mystery and scaling it up to cosmic proportions. What if dark energy isn't just an impersonal force, but something far more profound? The universe's own form of awareness, subtly shaping the fabric of existence. This idea straddles the line between radical science and ancient philosophy, suggesting that the cosmos might not just contain consciousness but embody it. At first glance, the notion seems lifted from science fiction, yet some quantum physicists have flirted with similar ideas for decades. The observer effect in quantum mechanics, where particles behave differently when measured, hints that consciousness might play a role in determining reality. Scale that up, and you could argue the universe's expansion isn't a mindless process but a deliberate unfolding, with dark energy as the mechanism by which cosmic intent manifests. Think of it like a dreamer shaping their dream. The universe's awareness, however alien to our own, might be the invisible hand guiding its growth. The parallels with Eastern philosophies are striking. Hindu cosmology describes Brahman as the universal consciousness that breathes worlds into being, while Taoist texts speak of the cosmos as an organic, self-regulating whole. Even modern panpsychism, the view that consciousness is fundamental to all matter, echoes these ancient intuitions. If even atoms possess a rudimentary form of awareness, as some theorists suggest, then dark energy could be how the universe's collective mind expresses itself on the grandest scale. Critics dismiss this as pseudoscience, and rightly so. There's no empirical evidence linking dark energy to consciousness, but the tantalizing overlap between physics and metaphysics persists. Certain interpretations of quantum gravity suggest that spacetime itself might emerge from deeper information processing networks, like a cosmic computer running the code of reality. In this view, dark energy's acceleration could be a byproduct of that underlying computation, a glitch or feature in the universe's operating system. The implications are dizzying. If consciousness and dark energy are somehow linked, it would mean the universe isn't just alive, it's awake. The same force pushing galaxies apart might also be the substrate of cosmic thought, a silent sentience humming beneath the surface of reality. Future experiments might never prove this connection, but the mere possibility invites us to rethink our place in the cosmos. Are we passive observers or fleeting sparks of awareness in a universe that's itself aware? The answer, like dark energy, remains shrouded in mystery, but the question alone stretches the boundaries of what science dares to imagine. Proving the universe breathes sounds like a task for cosmic detectives, and scientists are already assembling the tools to crack the case. The key lies in hunting for patterns hidden in the fabric of spacetime itself, clues so subtle they've eluded us for decades. Imagine trying to measure a heartbeat from light years away, where every pulse takes billions of years to complete. That's the challenge astronomers face as they design instruments sensitive enough to catch dark energy's rhythm in the act. Next-generation telescopes like the Vera Rubin Observatory and ESA's Euclid mission are game-changers. By mapping billions of galaxies across unprecedented distances, they'll track how dark energy's push has varied over cosmic history. Think of it like watching a slow-motion film of the universe's expansion, frame by frame. If dark energy's strength oscillates, growing slightly weaker in some epochs, stronger in others, it could betray the universe's respiratory cycle. Even a 1% fluctuation over 10 billion years would be enough to send theorists back to their chalkboards. These telescopes won't just take snapshots, they'll create a time-lapse of the cosmos, searching for the telltale accelerations and decelerations of a breathing universe. Gravitational wave astronomy adds another layer to this hunt. When black holes collide, they send ripples through spacetime that detectors like LIGO and the Future Laser Interferometer Space Antenna can catch. But here's the twist: as these waves travel across an expanding universe, dark energy subtly alters their frequency. If the universe's expansion rate fluctuates, speeding up or slowing down like a lung filling and emptying, those gravitational waves would carry an echo of that rhythm. It's akin to listening to a song played on a record that keeps changing speed. The distortions reveal the turntable's hidden behavior. A pattern in those distortions could be the smoking gun for cosmic breath. Some of the most tantalizing evidence might come from the cosmic microwave background's fine details. The Atacama Cosmology Telescope and Simon's Observatory are scanning this ancient light for polarization patterns that could encode dark energy's early behavior. If the universe's inhale phase began before the Big Bang, as cyclical models suggest, its gravitational imprint might linger in these photons like a fingerprint on glass. Other teams are studying quasars, whose light bends through intervening galaxies in ways that could reveal if dark energy's strength varies across space, not just time. The real breakthrough may come from combining all these approaches. Just as doctors cross-reference X-rays, blood tests, and EKGs to diagnose a heart condition, cosmologists need multiple lines of evidence to confirm the universe's breadth. A fluctuation in supernova brightness here, an anomaly in gravitational wave data there, a strange correlation in galaxy clustering. Only when these pieces align will the picture emerge. It's painstaking work, but the payoff would rewrite our cosmic story. Instead of a universe winding down toward cold oblivion, we might live in a cosmos that's eternally alive, its expansion and contraction as natural as the tide. What makes this quest so thrilling isn't just the science, it's the sheer audacity of the question. We're not just asking what the universe is made of, but whether it moves with the cadence of life itself. And with every new instrument we point skyward, we're one step closer to feeling that cosmic pulse. Dark matter and dark energy might seem like opposing forces, one pulling the cosmos together, the other tearing it apart, but their dance could be the universe's way of breathing. Picture a pair of cosmic lungs. Dark matter acts like the diaphragm, its gravitational pull drawing galaxies inward like an inhale, while dark energy's repulsive push mimics the exhale, stretching space-time outward. This delicate balance doesn't just shape the universe's structure, it could be the hidden rhythm behind everything from galaxy clusters to the voids between them. The evidence for this cosmic tug-of-war is etched into the night sky. Dark matter's gravity sculpts galaxies into spirals and ellipticals, binding them in vast clusters that resemble nodes in a sprawling respiratory system. Without it, galaxies would fly apart like dust in the wind. Yet dark energy counters this pull, creating expansive voids where matter thins out, as if the universe were holding its breath between cycles. The interplay between these forces isn't random, it's precise, like the calibrated tension between inhaling and exhaling that keeps a living body alive. Too much dark matter and the universe would collapse inward, too much dark energy and it would rip itself apart. Instead, they exist in a dynamic equilibrium, as finely tuned as the gears of a cosmic clock. What's fascinating is how this balance changes over time. In the universe's youth, dark matter dominated, its gravity fostering the birth of stars and galaxies. But as expansion accelerated, dark energy took the lead, its influence growing as space stretched. Some theories suggest this shift wasn't accidental. It might follow a deeper pattern, like the slow transition from inhalation to exhalation. Simulations show that slight variations in the dark matter to dark energy ratio could drastically alter cosmic evolution, leading to universes either too dense or too sparse for life. Our universe's perfect calibration hints at something extraordinary, a system that regulates itself, almost like a living organism maintaining homeostasis. Critics argue that calling this interplay breathing is just a metaphor, but the parallels run deeper than poetry. Recent studies of galactic filaments, those thread-like structures connecting galaxy clusters, reveal flows of gas and stars moving in ways that mirror fluid dynamics in biological systems. Dark matter's gravitational currents channel matter like airways directing oxygen, while dark energy's push creates the cosmic equivalent of alveolar sacs, vast voids where expansion is most pronounced. Even the timing aligns. The universe's transition from matter-dominated to energy-dominated eras resembles the switch from anaerobic to aerobic respiration in early life, marking a shift to more sustainable energy use. The implications stretch beyond cosmology. If dark matter and dark energy truly operate in cyclical tension, their interplay could redefine our understanding of cosmic evolution. Instead of a linear march toward heat death, the universe might follow a rhythm of gathering and release, contraction and expansion. Future missions like NASA's and Nancy Grace Roman Telescope aim to map dark matter's distribution in unprecedented detail, while gravitational wave observatories could detect how dark energy alters spacetime's vibrations. Together, these tools might reveal whether the cosmos is truly breathing, and if so, how deeply. What's at stake isn't just a scientific model but a paradigm shift. For centuries, we've seen the universe as a machine, cold and unfeeling. But if dark matter and dark energy are partners in a cosmic respiratory cycle, then reality might be more alive than we ever dared imagine. A vast, pulsing entity where even the emptiest voids are part of a grand, eternal breath. If our universe truly breathes, expanding and contracting in a cosmic rhythm, why should it be alone in that dance? The multiverse hypothesis suggests countless other universes might exist beyond our own, each with its own unique physics, its own tempo of breath. Picture an infinite orchestra where every universe plays a different note, some expanding rapidly like a trumpet's blast, others contracting slowly like a cello's hum. In this grand symphony of realities, dark energy wouldn't be a fixed force but a variable, stronger in some universes, weaker in others, or even absent entirely. Our universe's acceleration might just be one possible cadence in a spectrum of cosmic respiration. The idea isn't as far-fetched as it sounds. Inflationary cosmology, the leading theory for the Big Bang, implies that new universes could constantly bubble into existence, each with slightly different fundamental constants. Some might collapse instantly, their breath cut short by gravity's grip. Others could stretch so thin that dark energy rips them apart before stars ever form. A rare few, like ours, might strike the perfect balance, dark energies push gentle enough to allow galaxies, planets, and life to emerge. This Goldilocks scenario raises a tantalizing question. Is our universe's breath special, or just one variation in an endless cosmic chorus? String theory adds another layer of intrigue. If the extra dimensions it proposes fluctuate across the multiverse, dark energy's strength could depend on how those dimensions curl and vibrate. Imagine a cosmic accordion with infinite settings. Some universes might have tightly wound dimensions, making dark energy weak and their expansion sluggish. Others could have looser configurations, letting dark energy roar and their space stretch at breakneck speeds. Our universe's expansion rate, then, wouldn't be a law but an accident of dimensional geometry, a single arrangement in an infinite tapestry. The implications are dizzying. If dark energy varies across the multiverse, it could explain why its measured value in our universe seems so improbably fine-tuned for life. Most universes might be stillborn or barren, their dark energy either too weak to prevent collapse or too strong to allow structure. We'd find ourselves in one of the rare realities where the breath is just right, not because of design, but because endless trials inevitably produce a few lucky winners. This anthropic reasoning is controversial, but it offers a way to reconcile dark energy's apparent fine-tuning without invoking a creator. How could we ever test such a wild idea? Direct observation is impossible by definition. Other universes lie beyond our cosmic horizon, but math and indirect clues might offer hints. If the multiverse exists, the statistical distribution of dark energy values across universes should leave subtle marks on our own reality. Anomalies in the cosmic microwave background, like the infamous cold spot, could be bruises from collisions with other bubble universes in the distant past. Even the large-scale structure of galaxies might encode echoes of neighboring realities, their gravitational tugs warping our universe's web in detectable ways. The most profound consequence isn't scientific but philosophical. A breathing multiverse demotes our universe from a singular masterpiece to a single stanza in an endless poem. Yet it also elevates our existence into something miraculous, a fleeting harmony in the cacophony of possibilities. Whether by chance or necessity, we find ourselves in a universe that breathes at just the right pace to let us witness it. And if dark energy's rhythm is indeed one among many, then every star, every atom might be a note in a symphony so vast, even the cosmos itself is just learning to listen. For centuries, science has painted the universe as a vast machine, cold, indifferent, governed by mindless laws. But if the cosmos breathes, expanding and contracting like a living thing, that sterile image shatters. Suddenly, we're left staring at something far more intimate, a universe that moves with rhythm, perhaps even purpose. This isn't just a shift in physics, it's a seismic tremor in philosophy, forcing us to ask whether existence is a clockwork accident or something closer to a grand, unfolding intention. Consider what it means for reality to pulse like a heartbeat. Machines don't breathe, organisms do. If the universe shares this fundamental trait with life, it blurs the line between cosmos and creature, suggesting a continuity that runs deeper than we imagined. Ancient Stoics envisioned the universe as a living being, its order reflecting divine reason. Modern panpsychists argue consciousness might be woven into the fabric of reality itself. Now, dark energy's rhythmic push offers a tantalizing bridge between these ideas and empirical science, a universe that doesn't just exist, but inhales and exhales with slow, deliberate cadence. Yet purpose isn't the only possibility. Nature loves cycles that require no guiding hand. Seasons turn, tides rise and fall, all driven by impersonal forces. Could the universe's breath be equally blind? The beauty of this view is how it reconciles grandeur with austerity. A breathing cosmos can inspire awe without demanding divinity, its majesty emerging from simple rules playing out across eternity. Fractals don't need a designer to weave their intricate patterns. Perhaps the universe's expansion and contraction arise from equally self-organizing principles, beautiful but meaningless. This duality forces us to confront humanity's place in the grand scheme. If the universe breathes with intent, are we mere spectators or participants? Some indigenous cosmologies describe humans as the universe experiencing itself, our consciousness a spark of cosmic self-awareness. Alternatively, if the rhythm is mechanical, we're fleeting accidents in an endless cycle, destined to dissolve and reform without memory. Both perspectives unsettle our anthropocentric hubris, reminding us that whether the universe lives or merely pulses, it operates on scales that dwarf human notions of significance. The ethical implications ripple outward. If the cosmos is alive, even metaphorically, does it deserve respect? Environmental ethics expand to cosmic proportions, challenging us to see Earth not as a lonely rock but as a cell in a vast organism. Pollution and climate change become more than local crises, they're disruptions to a planetary system nested within something even greater. Conversely, if the universe is indifferent, our responsibility sharpens. We alone must assign meaning, knowing no higher purpose will save us from ourselves. What's thrilling is how science and philosophy converge here. Dark energy's mysteries aren't just equations to solve, they're mirrors held up to our deepest questions. Whether the universe breathes by chance or design, the mere possibility reshapes how we see existence, blending physics and metaphysics into a single, unanswerable wonder. And perhaps that's the most profound consequence of all, not certainty, but the stirring realization that reality is stranger, richer, and more mysterious than we ever dared dream. Long before telescopes sliced the night sky into data points, humanity's oldest stories whispered a startling truth: the cosmos breathes. Norse shamans spoke of Yggdrasil, the immense world tree whose roots and branches connected realms, pulsing with the sap of existence like a celestial circulatory system. The Aboriginal peoples of Australia sang of the rainbow serpent, an astronomical being whose undulating body carved rivers and galaxies alike as it moved through dreamtime. These aren't mere myths, they're sophisticated models of a living universe, encoded in oral traditions that predate modern cosmology by millennia. What's astonishing isn't their poetic beauty, it's their eerie alignment with cutting-edge physics, as if our ancestors glimpsed dark energies dance through the veil of metaphor. Consider the Hindu concept of prana, the breath of the universe that flows through all things. Ancient texts describe cosmic cycles of inhalation and exhalation lasting billions of years, with universes dissolving and reforming like bubbles in a vast ocean. Modern Big Bounce theories echo this almost verbatim, replacing prana with quantum vacuum fluctuations but preserving the same rhythmic structure. Or take the Mayan long count calendar, which measured time in sprawling 26,000-year cycles resembling the universe's hypothesized respiratory period. These parallels defy coincidence, suggesting indigenous knowledge systems encoded observational wisdom modern science is only now decoding with particle accelerators. The Dogon people of Mali present perhaps the most baffling case. Their astronomical traditions, dating back over 7 centuries, describe Sirius as a binary star system, a fact confirmed by telescopes only in the 19th century. Even more remarkably, their creation myths speak of a primordial egg of the world vibrating with energy before exploding outward, an uncanny precursor to both Big Bang theory and oscillating universe models. Similar threads weave through Maori navigation chants that treat celestial bodies as ancestors, Cherokee stories of a breathing earth, and Babylonian epics where the god Marduk slices the chaos monster Tiamat to fashion the heavens, a narrative mirroring how quantum fluctuations may have seeded galactic structures. This convergence raises profound questions. Were these myths simply lucky guesses, or did ancient cultures access modes of knowledge beyond our current framework? Some anthropologists propose that prolonged exposure to unpolluted night skies allowed pre-industrial societies to detect subtle cosmic patterns invisible to our light-drowned eyes. Others suggest trance states or plant medicines opened perceptual gateways to universal truths. Whatever the explanation, the overlap challenges the assumption that science alone holds the keys to reality's mysteries. When Lakota elders describe the Milky Way as the breath of the Great Spirit, they're not just crafting poetry, they're articulating an intuitive grasp of dark energy's animating force, expressed through the language available to them. The implications ripple beyond academia. If modern cosmology is rediscovering what indigenous cultures never forgot, it demands we rethink the hierarchy between hard science and myth. Perhaps both are mapping the same terrain with different tools, one through equations, the other through metaphor. As physicists grapple with dark energy's enigmas, they might find unexpected allies in these ancient traditions, not as literal truth but as resonant signposts pointing toward deeper patterns. The universe's breath may have been felt long before it was measured, its rhythm humming beneath humanity's collective imagination like a song half remembered across centuries. What emerges is a vision of science not as a break from tradition, but as its continuation, a new dialect in an eternal conversation about the living cosmos. The next breakthrough in understanding dark energy might come not just from a lab, but from some long-overlooked verse of the Rig Veda or an elder's star story passed down through generations. These cultural echoes remind us that the universe's greatest secrets often hide in plain sight, woven into the very stories we've told ourselves since the first campfires flickered against the dark. If the universe breathes, then every atom in our bodies, every star in the sky, is part of a vast living system, and suddenly, environmental ethics isn't just about saving trees, but about honoring a cosmic kinship. This shift in perspective turns pollution from a local problem into a violation of something sacred, like dumping trash into the lungs of a god. Indigenous cultures have understood this for millennia. The Maori concept of Wakapapa traces all existence back to a single ancestral source, binding humans to mountains and galaxies alike. Modern science might be catching up, revealing how Earth's biosphere mirrors galactic structures, with fungal networks mimicking dark matter filaments and ocean currents echoing interstellar plasma flows. If the universe is alive, then sustainability isn't just practical, it's spiritual. But this raises unsettling questions. Would a living universe even notice our destruction of Earth any more than we notice the death of skin cells? Some argue that cosmic scales render human actions insignificant. A single exhale of the universe lasts billions of years, far beyond our species' lifespan. Yet others counter that consciousness might operate at all scales, making our planetary stewardship a meaningful act within the greater whole. Think of it like the microbiome in your gut. Those bacteria don't comprehend you, but their health affects yours. Similarly, our treatment of Earth could ripple through dimensions we can't perceive, influencing the universe's larger breadth. The practical implications are profound. Legal systems could evolve to recognize ecosystems as living entities with rights, as Ecuador's constitution already does for its Pachamama, Mother Earth. Space exploration might prioritize non-interference protocols, treating other planets not as resources to mine but as organs in a cosmic body. Even urban design could change, with cities built as fractals that harmonize with natural patterns rather than dominate them. Architects like Buckminster Fuller envisioned this decades ago, designing structures that mirrored atomic lattices and planetary orbits, blueprints for a civilization in sync with a breathing cosmos. Critics warn against anthropomorphizing the universe, equating it to New Age mysticism. But the boundary between metaphor and mechanism is blurring. Biologists now study how slime molds solve mazes and fungi transmit electrical signals, challenging definitions of intelligence. If simple organisms display problem-solving behaviors, why not galaxies? The Gaia hypothesis, once ridiculed for suggesting Earth self-regulates like an organism, now underpins climate science. Perhaps the breathing universe theory is the next step, not a rejection of rigor, but an expansion of what life can mean. Ultimately, this perspective doesn't demand we abandon science for spirituality, but that we marry the two. A telescope and a sweat lodge can ask the same question. How do we belong to something greater? The answer might lie in dark energy's ebb and flow, a reminder that we're not just observers of the universe, but participants in its breath. Every choice, from planting a tree to launching a satellite, becomes part of that rhythm, a heartbeat within the cosmic body. The next decade will transform our understanding of dark energy, thanks to a new generation of cosmic explorers poised to launch into the void. ESA's Euclid spacecraft, already sweeping the skies with its razor-sharp infrared gaze, isn't just another telescope, it's a time machine dissecting 10 billion years of cosmic history. By mapping the precise positions of 2 billion galaxies across 1/3 of the observable universe, Euclid will trace how dark energy's push has warped the cosmic web over eons. Its measurements are so precise they could detect variations in dark energy's strength equivalent to spotting a human hair from 10 miles away. If the universe truly breathes, Euclid might catch its chest rising and falling in the subtle way galaxy clusters stretch and compress across deep time. NASA's Nancy Grace Roman telescope, set to join this cosmic detective work in the mid-2020s, brings an even wilder capability. It will stare at the same patch of sky for months, capturing ultra-deep 3D snapshots of space-time's curvature. Imagine taking a slow-motion video of a pond's surface to study every ripple. Roman will do this for the fabric of reality itself. Its wide-field instrument can photograph an area of sky 100 times larger than Hubble's famous deep field in a single exposure, revealing how dark energy's influence changes not just over time, but in different directions. Should the universe's breath come faster in certain regions like lungs expanding unevenly, Roman's unprecedented cosmic cartography will expose these asymmetries. But the real game-changer lies in combining these missions with revolutionary ground-based observatories. The Vera Rubin Observatory's legacy survey of space and time will image the entire southern sky every 3 nights for a decade, creating a stop-motion movie of the cosmos where blinking quasars and exploding supernovas serve as mileposts for measuring dark energy's grip. Meanwhile, the Dark Energy Spectroscopic Instrument is cataloging 35 million galaxies' precise redshifts, essentially taking the universe's temperature to see if dark energy fluctuates like a fever. Together, these projects form an interlocking web of observation powerful enough to spot deviations in cosmic expansion down to 1 part in 10,000. The equivalent of noting if a marathon runner's pace varies by half a second over the entire race. What makes this moment historic isn't just the technology, it's the potential to witness dark energy's behavior changing in real cosmic time. Current theories make starkly different predictions. If the breathing universe model holds, these telescopes should find dark energy's strength oscillating in a slow sinusoidal pattern. A constant dark energy would show linear acceleration, while phantom energy scenarios predict an exponential spike. The data could even reveal something nobody predicted. Perhaps dark energy interacts with dark matter, or its effects vary in strange periodicities that hint at extra dimensions. Like doctors finally isolating a mysterious vital sign, cosmologists may soon have their first clear read on the universe's pulse. The implications ripple far beyond academic journals. If these missions confirm dark energy fluctuates cyclically, it would rank among the greatest scientific paradigm shifts since Copernicus, proof that the cosmos operates less like a clock and more like a living system. Funding agencies might pivot to study cosmic seasons, while philosophers grapple with a universe that renews itself. Conversely, if dark energy remains stubbornly constant, the breathing universe hypothesis could collapse, forcing theorists back to the drawing board. Either outcome would rewrite textbooks, but the true prize lies in the surprises, those unexpected data points that often lead to the deepest revelations. What's thrilling is how accessible this revolution will be. Citizen scientists can already join the hunt through projects like Zooniverse, classifying galaxy shapes to help train machine learning algorithms. Amateur astronomers with backyard telescopes contribute valuable supernova observations that refine dark energy measurements. In an era where cosmic discoveries once required billion-dollar facilities, the next breakthrough might come from a high school student spotting an anomaly in publicly available telescope data. This democratization of cosmology mirrors how 17th-century telescope technology empowered amateur astronomers like William Herschel to discover Uranus. Except now, everyone with an internet connection can probe the universe's breadth. The coming flood of data won't just answer old questions, it will expose gaps in our understanding we can't yet articulate. Like the first microscopes revealing a hidden world of microbes, these new instruments will likely uncover phenomena that redefine what we consider possible. Perhaps we'll find evidence of previous cosmic cycles etched in gravitational waves, or detect strange correlations between dark energy and quantum entanglement. Whatever emerges, one thing is certain: humanity stands on the threshold of seeing the universe not as a static backdrop, but as a dynamic, perhaps even living entity, and the telescopes launching this decade will be our first real chance to listen to its heartbeat. You don't need a billion-dollar telescope to help unravel the mystery of dark energy. Some of the most important cosmic discoveries start in backyard observatories and living rooms. When a star explodes as a supernova billions of light years away, that cataclysmic flash becomes a cosmic yardstick for measuring how fast the universe is stretching. The catch: scientists need eyes everywhere to catch these fleeting stellar fireworks, and that's where amateur astronomers and citizen scientists step onto the cosmic stage. By simply pointing telescopes at patches of sky or sifting through galaxy images online, everyday people are contributing to one of cosmology's grandest quests, deciphering whether the universe breathes. Take the Zooniverse platform, where volunteers have classified millions of galaxy shapes and light patterns that even advanced algorithms struggle to interpret. One retired schoolteacher in Portugal spotted a peculiar supernova in 2014 that professional surveys missed. Its unusual light curve later helped calibrate dark energy models. Then there's the American Association of Variable Star Observers, a global network of backyard astronomers whose meticulous records of stellar brightness changes have refined how we measure cosmic distances. These aren't just hobbyists, they're the front line of a scientific revolution, proving you don't need a PhD to move humanity's understanding of the cosmos forward. The magic lies in supernova type 1a stellar explosions so consistent in brightness they're called standard candles. When these detonations flicker to life, their apparent brightness tells us how far away they are, while their redshift reveals how much the universe has expanded since the light began its journey. By comparing thousands of these measurements across different eras of cosmic history, scientists map dark energy's influence like detectives reconstructing a crime scene. But with only a handful of professional telescopes scanning the skies, most supernova would vanish unnoticed without amateur contributions. A single high school student in Japan using a modest 8-inch telescope recently logged a critical supernova in the Whale galaxy, data now woven into official dark energy calculations. What's exhilarating is how accessible this research has become. Projects like Supernova Hunters on Zooniverse train volunteers to identify potential explosions in real telescope data within minutes. Other initiatives like the Los Cumbres Observatory's Global Telescope Network let anyone request time on robotic telescopes to track cosmic events. Even smartphone apps now alert users to sudden bright spots in nearby galaxies, turning night sky enthusiasts into instant cosmic first responders. The result: a democratization of discovery where a farmer in Australia might spot a supernova between harvests, or a nurse in Norway could help classify galaxy clusters after night shifts. The implications go beyond data collection. Every new supernova logged builds a richer timeline of the universe's expansion, helping scientists discern whether dark energy's push follows a steady rhythm or fluctuates like breath. Some citizen-contributed observations already hint at tantalizing anomalies, supernova in certain galactic environments appearing slightly dimmer than expected, possibly indicating dark energy's strength varies across spacetime. While not yet conclusive, these grassroots discoveries are steering professional researchers toward new questions, proving that cracking cosmic mysteries isn't just for elite institutions. This collaborative spirit mirrors how science used to work centuries ago, when wealthy naturalists and amateur stargazers advanced knowledge together. Only now the tools are cheaper, the networks global, and the stakes higher. As dark energy telescopes like Euclid and Roman come online, they'll generate more data than any team of professionals could handle alone. The solution: a planet-sized team of curious minds, each adding their piece to the puzzle. Whether you're sketching galaxy clusters from a suburban balcony or analyzing telescope feeds on a lunch break, you're part of a grand human endeavor, listening for the heartbeat of the cosmos.